make sure that everybody has time to wander in before we get started. Everybody for finding us in this non-traditional location today. And thanks for everybody's flexibility on that. So it is my pleasure this morning to introduce Ruth Angus. Dr. Angus is a familiar face. She did a pre-doc here at the CFA, which is good news for me as a host because it means that she is fluent in Pratt and Phillips and A building and B building and is able to kind of navigate her way around this space. She currently holds a number of titles. Assistant Curator and Professor in the Department of Astrophysics at the American Museum of Natural History. Associate Research Scientist at Flatiron and Assistant Adjunct Professor at the Department of Astronomy. And today Dr. Angus is going to be telling us about the ages of stars.
Thank you. Okay, I just wanted to start by saying it's really nice to be back here. It's been about 4 years since I was last here, and my geography of the buildings is definitely decaying over time. So I took a few wrong turns getting between Pratt and here. But I just wanted to say, so before I was a pre-doc here, I was also here as an undergraduate on the Southampton Exchange. Some of you might know other students who've come through that program. And I think that was really important for me when I was kind of a senior in college, and then it led to me coming back as a pre-doc. And the time that I spent here was very influential for my whole career, and I met lots of people and made lots of collaborations that I'm still continuing today. Okay, so I do have a lot of titles. I just wanted to take a second to explain exactly what my kind of positions are. So my home institution is the American Museum of Natural History. That is where I am chiefly appointed. And I'm sure many of you have been there. My office is up there, so I look over the planetarium. I am currently half-time at Flatiron, in the Flatiron Institute, which is not in the Flatiron building. If any of you ever come and visit, sometimes people go to the Flatiron building by accident. We're just around the corner. And I will be half-time there for now the next 4 years, but after 4 years, I will go just full-time at the museum when I go up for tenure, if I get tenure. And then all of the curators at the museum have adjunct appointments at Columbia, which means we can advise graduate students through the Columbia grad program, and we do a small amount of teaching there. I should just briefly advertise the fact that the planetarium has a new space show, which is starting January 21st. It's about the solar system. It's going to be narrated by Lupita Nyong'o. So come check it out. It's not very far away. One more advertisement. We are hiring. There are many opportunities currently at AMNH and Flatiron if you are on the job market this year. There are also faculty positions. Flatiron's hiring a joint position with NYU. We're hiring 2 postdoc positions at the museum to work on TESS and stellar astrophysics. One of the ads is on the job register now. Okay, so I'm going to talk today about measuring stellar ages. And I've really been finding, as I sort of talk to people generally at conferences, I find that stellar ages is really something that a lot of people care about. Lots of people are very interested in having more precise ages for a larger number of stars. Having some kind of large-scale age catalog. These are products that are really useful for the community. And when I think about stellar ages, and what I'm kind of talking about today is going to be mostly relevant for the kinds of stars that host exoplanets, which also happen to be the most difficult stars to measure ages for. So, stellar ages are hard to measure, especially if they're on the main sequence, and especially if they're cool. It gets harder the cooler you go. And just a point of clarification, I only work on sort of field stars. I'm not talking about measuring ages for stellar populations. I'm not talking about fitting isochrones or turn-off ages to populations of stars. I'm really just talking about what do you do if you have a field star and you want to know its age. How can you measure the best age for that star? So here is a illustration of why stellar ages are difficult to measure on the main sequence. So this is a stellar evolution track for the sun. When the sun's very young and when it turns off the main sequence, it moves really quickly in this space on the Hertzsprung-Russell diagram. And so that's useful if you want to measure the age of a star that is very young or pre-main sequence or post-main sequence. Stars like that evolve very quickly, and we can measure their ages quite precisely, but when they're on the main sequence, they just don't change very much over time. And so it's really difficult to measure their ages using stellar evolution models and isochrones. And unfortunately, if we want to understand the evolution and formation of planetary systems, this is kind of tough because most of the planets that we have discovered to date live around main sequence stars. Although I should point out that there have been planets discovered around subgiants, and Sam Grunblatt is a postdoctoral fellow at the museum who is currently searching for new planets orbiting subgiants. These are going to be astroseismic stars, so you can get very precise ages for these stars because they're pulsating and they're moving quickly on the Hertzsprung-Russell diagram. And there are also, people have also found planets around young pre-main sequence stars. For example, Elizabeth Newton and Trevor David have recently discovered some very young planetary systems. And Trevor David is starting, I think he started as a Flatiron Fellow earlier this week. Okay, so that's kind of why ages are difficult to measure on the main sequence. And I think if we're kind of trying to plan ahead, think about how we can make things easier for ourselves, I think there are really three angles of attack for improving stellar ages. The first is that we can think about combining dating methods. So there are lots of age indicators available for lots of stars. In fact, pretty much every star, thanks to Gaia, has two. So Gaia provides precise photometry, so apparent magnitudes, parallaxes, and colors, and it provides proper motions. And you can get an isochronal age for every star in Gaia by fitting its position on the CMD to an isochrone, and you can get a kinematic age for every star in Gaia. So already you can combine those two things and improve ages that you measure from either one individually. I'm focusing in this talk on combining isochrone fitting with more precise stellar dating methods like gyrochronology, rotation dating. I'll get to that in a second. The second thing that we can do to improve stellar ages is, of course, improve our models. This involves, improving our understanding of stellar astrophysics and stellar evolution models, but also improving many of these empirical age relations that we can use that are very powerful because they can be very precise, but currently they suffer from being poorly calibrated. And then finally, the last thing I think we can do to improve ages is to improve measurement precision. And a lot of this involves some hardware improvements and new surveys. But there's also some software improvements too. So something that I focus on a lot is measuring stellar rotation periods. And there's still a lot of improvement we can do with measuring stellar rotation periods that will lead to more precise stellar ages. So these are kind of the three main things I think are important for improving ages. You can kind of think of it as like software, physics, and hardware. Those are the three things we could improve. So coming up in this talk, these are the three things we're going to talk about. I probably won't get to this one, but I'm going to talk about it in the ITC lunch. Okay, combining dating methods. So here's kind of a picture of what you would actually do if you have a star, say you have an exoplanet host, and you want to measure its age. Traditionally, you'll probably work in this space, so absolute magnitude and color, and you'll place your star down in this space, and you'll fit an isochrone to the position of your star and estimate a stellar age. It gets easier if your star's up here, because Measurement uncertainties mean that your star will almost always overlap with many isochrones. So when your star's up on the subgiant, it's evolving off the main sequence, the isochrones are spaced very widely apart, and your uncertainties will only overlap with a few possible ages. If you're down here, it's basically impossible to measure a stellar age with this method. So for Ks and M dwarfs, you pretty much can't constrain their ages within the age of the universe. So this kind of dating just doesn't work for those stars. We have to do something else. We can get precise ages for stars turning off the main sequence and imprecise ages getting worse as you go cooler for main sequence stars. Here's another approach that people take to measuring ages. Often, again, if you have a planet host, if you found the planet with the transit method, then you might also be able to measure a rotation period from the very same light curve that you used to detect the planet, in which case you can place it down in this space. So these are also isochrones that I'm showing, but this is rotation period versus effective temperature. Stars lose angular momentum over time, so they evolve upwards in this diagram. So if you measure a rotation period for your star, you can place it down here, and you can infer an age. Typically, the uncertainties that you measure when you're measuring a rotation period are small. And so it's actually pretty easy to have a data point with uncertainties that only overlap a few isochrones. This is why gyrochronology, this process of measuring ages with rotation periods, is so precise. The isochrones are quite spread out relative to the uncertainties on the measurements. So this is just information theory, but this is why gyrochronology can be so precise. That's a really good question. So how do I know the initial period of the star? Yeah, so I'll explain a little bit in more detail later, and hopefully it'll become clearer. But the basic idea is that stars actually forget their initial rotation period after about, it depends on the mass, but 100 million years or so, because there's this feedback between angular momentum loss rate and rotational speed. Rotation generates magnetism, which leads to efficient angular momentum loss. I'll explain it in more detail later, but basically, after about 100 million years, most stars have forgotten their initial rotation periods. That's actually not true for M dwarfs. That's why this works so well. Okay, so we can put this all together. So we can use isochrones on the color magnitude diagram, and we can use rotation periods, and we can model both things at once and get more precise ages. The really good advantage of combining isochrone fitting with rotational evolution is where one is precise, the other is imprecise. So isochrone fitting gives you precise ages on the subgiant branch, but rotational evolution doesn't. It's not very well calibrated there. Rotational evolution also doesn't give you precise ages for hot stars. But it does give you really precise ages on the main sequence. So these two methods are really complementary. Actually, you can see, so for these kind of Gs and Ks, the isochrones are very spread out here, but as you get hotter, they get closer together. So for hot stars, this doesn't work as well. It still works pretty well. I just wanted to say I'm not going to talk about it in detail today, but that measuring a rotation period from a light curve, which we do through a combination of, there are many different methods we can use. That's just one summary statistic of a light curve. And there's actually a lot of other information in light curves that tell us about stellar properties that we're not using currently. So this is kind of, there are many people have been thinking about this, but Melissa Ness has really led the effort on trying to extract other information from light curves that tell us about stellar properties. Oh, and Fabienne Bastien's work on flicker is another example of this. So flicker is short timescale variability in the light curve that's caused by granulation. That tells you about age. So there's a lot more work that we can do with converting light curves to ages, but I don't really have time to go into it. Okay, here is some real data. So these are stars on a color magnitude diagram, a Gaia color magnitude diagram. These are stars from Amy McCullen's 2014 catalogue of Kepler rotation periods. And the points are colored by their rotation period. And this is where you can kind of see how this rotational evolution is happening. If I zoom into the main sequence, you can see that across the main sequence, there is a gradient in rotation periods. And that's because stars spin down as they get older. Okay. So a few weeks ago, a paper describing this method was on the archive. So this is a software package that I developed called Stardate, which combines isochrone fitting and gyrochronology, rotation dating. And all you need in order to measure an age for your star is information you can get from Gaia, just apparent magnitudes and parallaxes, and a rotation period. If you don't have a rotation period, you should use isochrones, Tim Morton's Python package, to get an age. There are other tools too, but Stardate is built on top of isochrones. So if you don't have a rotation period, you don't gain any extra information using Stardate. But Stardate does the combination of isochrone fitting and gyrochronology for you. We use the MIST isochrones in this software package. This is the first, and I think only, software package that is available for gyrochronology, to my knowledge. And the reason for that is that gyrochronology, the relations between rotation period, age, and mass, used to be very simple. It was just a power law. But now they're getting complicated, and so we need software packages for people to be able to apply the relations in order to get ages. Okay, so let me just talk to you a little bit about the maths. So exactly what I'm doing. It's really quite simple. So this is kind of what goes on under the hood in Stardate. So for those of you who are familiar, these are probabilistic graphical models. If you're not familiar with them, then they still, I think, get the point across. These gray circles, these are observables, and the white circles are model parameters. And in probabilistic graphical models, you can think of these arrows as meaning that age, mass, metallicity, distance, extinction generate the observables. So they generate absolute magnitudes and colors. So traditionally, when people measure a stellar age, what they'll do is they'll probably try to calculate an age from isochrone fitting. And if they have a rotation period, they'll also try to calculate an age from gyrochronology. And usually people report both ages. They'll probably be a little different. They'll have different uncertainties. Sometimes people use other dating methods and they also report those ages. But it's difficult to know what you do. How do you combine those multiple ages? The way that we do it in Stardate is we just combine the likelihood functions. So you can just move rotation period in to the whole process. You don't have to keep it separated. Actually, in practice, what we do is we factorize this. So we actually assert that rotation period doesn't depend on metallicity, distance, and extinction. It just depends on mass and age. And there's just one age here. So age controls rotation period, and it controls position on the CMD. And so you just get a posterior for your single age of your star that takes into account all of the observables. Oh yeah, also, so rotation periods now can improve masses. With Stardate, if you have a rotation period, you can infer a mass for your star more precisely. And that's because rotation period depends on both age and mass. Okay, are there any questions about this? Yes, so Stardate will provide you with posterior distributions over mass, age, metallicity, distance, and extinction. So you'll get a metallicity. Metallicity doesn't strongly depend on rotation period, but it does depend on age and mass. So your metallicity you'll have a little bit of an improvement, not as much as you will from mass. But yeah, you do get a metallicity too. Yes, question here?
How do you deal with the rotation period dependence on latitude?
On latitude in the sky.
In the star?
Oh, in the star. We don't deal with that at all for now. The reason why that is really important and does come into things is because if you underestimate the uncertainty on your rotation period, you will underestimate the uncertainty on your age. So you really do, uncertainties on rotation periods are very important. They are age dependent. For now, we just assume that the rotation period we detect is some noisy observation of the true rotation period. Dave?
So this makes sense. The earlier thought about gyrochronology.
Yes.
Where are those curves coming from?
These curves. So these curves come from the Persepi cluster. So this is the gyrochronology model currently implemented in Stardate. It is a very simplistic model.
But I mean, they go up to 10 gigabits.
So it's extrapolation, pure extrapolation.
From what is?
So this relation between rotation period and temperature comes from Persepi.
Right.
And then if you add in the sun, you get 2 data points in age, right? This turns out to work really well for all of the clusters that we currently have rotation periods for. So I don't need to adjust the model to account for the clusters in between.
No, that's great. I guess what I'm saying is, given this plot, I have no doubt that from this plot, you can get a very precise age. But how much do you believe this plot? I get what you're saying downstream, but I want to understand how much you have confidence, because this is amazing.
Yes. Can we put a pin in that question? And I'm going to talk more about it in the second half of my talk. And maybe we can come back to it at the end. The short answer is, I don't trust this very much, and you'll see why. Roseanne.
I was just wondering about how you exclude binaries.
Mm-hmm.
Because in many cases, you might expect that the spin period is influenced by a companion, and in some cases, you may not know
Yeah.
the companion is there for a variety of reasons.
Yes. So we definitely do see that. So that here's the binary sequence on top of the main sequence, and you can see that their rotation period doesn't seem to depend on age very much. Some of these are synchronized binaries, so the rotation period will be rapid because it's the same as the orbital period of the system. Currently, Stardate does not account for binarity. So, for example, if I were going to measure ages for all the stars in the Macquillan catalogue, I would remove the binary sequence first. If you have...
It's just the ones that you didn't recognize were binaries.
Yeah.
Would they come up, would your answer turn out to be strange in some way?
Yes.
Or your estimated uncertainty large enough that you might put those aside and not be fooled by them?
Yes, they would. They would mess things up. Not all binaries, just ones that are sort of orbiting close together. Stephanie Douglas is an expert on how binarity influences gyrochronology. And there are certainly things we can do to improve the models. Like we could have a mixture model that would allow for outliers in our model. That's something that we could implement. For now, we don't deal with binaries. We could also, because in Tim Morton's isochrone package, he has a binary model. So it's a relatively minor upgrade, I think, to account for binarity. Okay. Okay. Yes.
When you have like a high metallicity in a star, it actually loses a lot of mass to the solar wind. And then does it affect your rotation period? Because it's just excluding, then actually not including let's say metallicity in your age estimation would naturally bring some errors in your computations.
Yes.
And I want to know how much your result is affected by the fact that you just don't consider that.
Right. So, metallicity does affect things in a couple of ways. It affects convection zone depth, which affects magnetic dynamo strength. Again, I'll sort of get to this in a little bit more detail. What we do here is we try to be conservative. So we actually switch gyrochronology off for stars where we don't think it's applicable or where it's not calibrated. And I'll explain how we do that, how we can switch it off. That means that we just get an isochrone age for those stars, not a gyrochronology age. And we do that for stars that are extremely metal poor or metal rich. So we just apply gyrochronology to stars that are kind of solar-ish metallicity, because it's just not calibrated for very high and very low metallicity stars. That was a good question. Okay, let me show you an example of stardate working. So these data come from Soren Maibaum's 2015 paper. This is NGC 6819. It's a Kepler cluster. It's a open cluster in the Kepler field, and it's about 2.5 billion years old. This plot shows the age for each star in that cluster treated as a single isolated field star. This dashed line is the sort of true cluster age. And for the F stars, you can see that the orange points, which are from isochrone fitting only, and the black points, which are from combining gyrochronology and isochrones, are very similar. And that's because for hot stars, isochrone fitting is quite precise. And so adding a rotation period doesn't actually add very much more information. So information theory kind of dictates which method will dominate the age information. So for hot stars and subgiants, isochrones provide the majority of the information and rotation periods don't. So isochrone ages will dominate there. But you can see as you go to cooler stars, there's this kind of envelope where the isochrones are getting spread further and further apart. And now rotational ages provide the most information, and they dominate. And you can see that although the isochrone ages for these stars are very poorly constrained, they have huge uncertainties. If you add in their rotation periods, you improve the age estimates significantly. Okay. And this is what I meant by even though we fit, this gyrochronology relation is only fit to Persephone in the sun, it's results like this that indicate that that's an okay thing to do, because we did not include this cluster in the fit, but it does predict good ages for this cluster. So back to this plot, and this is my point about switching gyrochronology off in certain areas. You can see that there are some areas where gyrochronology rotation just doesn't tell you very much about age. It doesn't tell you much down here. It doesn't tell you much up here. So we in these areas where gyrochronology isn't calibrated well, so for metal poor and metal rich stars and low mass stars, we inflate the variance. We artificially inflate the variance on the rotation period. So we say, like, we don't have any information about rotation. Now just use isochrone fitting to provide all of the age information in those areas. And so we have a metallicity cut where we do this. We have a color cut where we do this for the low mass stars. We have another one for the high mass stars. We have a cut in evolutionary stage. So in the missed isochrones, it's EEP. And we just switch gyrochronology off in those regions. This is something that we could improve because we actually haven't fit this to data. We've just kind of decided a little arbitrarily where we think gyrochronology doesn't work very well. We could fit this in principle. Yeah.
So Ruth, I was wondering, so you get the uncertainties from how you showed before, right, with the reference models. And why do your uncertainties work in this regime, and why do you have to artificially inflate them outside? Wouldn't your this data that already shows that you don't have information about that in that region should provide you? I guess my question is, how do you trust the uncertainty in this regime when in the regime where your data doesn't give you much information, you cannot?
Is this a question about whether or not we trust the uncertainties reported on the rotation periods?
No.
Or
No, the uncertainties that come from using the rotation periods as they are. So if you didn't inflate the uncertainties on the rotation periods and you used gyrochronology as well, you just end up with a higher uncertainty because gyrochronology didn't provide more information. than you already had.
Right.
But instead of doing that, you inflate the uncertainty of that regime. We can talk about that.
Can you try summarizing one more time? I feel like I almost understand what you're saying, but not quite.
Yeah, so I was, if I understood correctly, you are inflating the uncertainty in the gyrochronology information.
Yes.
Because that will not give you any extra information in some regimes.
It will give you extra information, but it will be wrong.
Okay.
And that's why we do it. Okay, was that your question? Okay, so we can't just, it's very difficult to say, like when we're combining these models, it's very difficult for us to say, in this region, just don't use gyrochronology. The reason why that's difficult is because if you have sharp changes in likelihood, it's very difficult to sample your posterior. And so what we do is we use smooth sigmoid functions so that the uncertainty on the rotation period inflates slowly. And that is essentially the same thing as just switching it off. And the reason we do that is just because if you don't do that, you'll still get gyrochronology predictions in these areas where you think gyrochronology doesn't work. And so they'll be wrong. Okay. So in some of these cases, we're rescued because isochrone fitting, as I keep saying, works very well up here. So it's all right that we switch off gyrochronology there. We'll still get precise ages with star date. It's all good. But down here, the gyrochronology relations aren't very well calibrated, and isochrone fitting is hopeless. So this is kind of our weak area, but we're working on it. And one of the ways in which we can probably significantly improve our understanding of M-dwarf age measurement is using activity. And activity would be relatively easy to add in here. We would do something like this. You can't independently add on activity because it is not independent from rotation. So you have to again be careful when you factorize your likelihood.
How do you define activity?
Oh, thank you. Good question. How do I define activity? On purpose, I'm being vague because activity indicators can take several forms. It can be calcium, H and K. It can be H alpha. It can be variability in the light curve. We actually know that scales with magnetic activity. I mean magnetic activity, to be clear. What else? Flare rates tell you about that activity, the magnetic activity of your star. So any of those things can go into this label that I've called activity. They all, with a broad brush, scale in the same way. They all relate to rotation period. And the activity is relatively easy to measure for M-dwarfs. We just need to calibrate the models better. And there are more things we could add in here. We could add in abundances. Abundances tell you about ages. We could add in kinematics. Kinematics, the velocities of stars, also tell you about their age. I'm going to talk a little bit more about that in a second, etc. There are other age indicators that you could add, but you get the idea. All of these things can be implemented in Stardate, and we are planning to add them. so that eventually you can just, have your list of all measurements for your star that contain age information and throw them into Stardate and improve your age estimate. Stardate we've tried to keep it as simple and easy to implement as possible. So it's built on top of isochrone. So this is what you would do if you were using Tim Morton's isochrones package. You give it all of the observables you have that relate to position on the Hertzsprung-Russell diagram. So any spectroscopic parameters, parallaxes, you can even add astroseismic parameters here. And then rotation period goes in, extinction can also go in. In the future, we're going to add more things that can go in there, and then you can just do star.fit, and you'll get an age posterior, and a posterior over mass distance extinction methodicity. Okay, to summarize this talk so far, if we want to get an age for every star, we really need to combine dating methods, because one method isn't going to give you an age for every star. You have to use multiple methods. And then Stardate is this open source project it's mostly for combining dating methods, but we are in the future planning to extend it to be a suite of codes and methods that all relate in some way to measuring a stellar age. Okay, that's part one. Let's just see how far we get with this second section. It should be short. Okay, improving models. This is a bit of a change of direction now. Now I'm going to talk about, okay, we can combine models. How do we make sure that those models are correct? There is loads of work in this area going on in New York. Almost all aspects of improving stellar models we are working on. I'm just going to talk about gyrochronology though. So, and the reason I'm so interested in gyrochronology is because it really is the most powerful one for main sequence stars. It by far gives you the most precise ages. It's really important that we calibrate it. Okay, so stars spin more slowly over time, but it's complicated. We used to think it was simple. Turns out that it's complicated. Here's the basic picture of what's happening. As stars contract on the main sequence, this is rotation period versus mass. They spin up. So that's what's happening now. These stars are moving down because they're contracting. Then after a certain time, they start rapidly converging onto a single track. And it's that convergence that allows us to be able to measure an age from a rotation period and a mass without needing to know the initial rotation period of a star. And this spin down is taking place because these stars have magnetic fields and they're breaking. They're losing angular momentum. Yeah, for the lowest mass stars, they take a really long. Yeah, I was oversimplifying. For the M dwarfs, it takes a really long time for them to converge. Yeah. There's another reason why M dwarfs are hard. Okay. Things actually are not this simple. So this is a paper from Jason Curtis. He shows that these three clusters, which have very different ages, actually are not evolving uniformly over time. This 1 billion-year-old cluster is actually right on top of the 5 or 670 million-year-old cluster. So something strange is going on there. One of the frustrating parts of gyrochronology is that the data that we need in order to calibrate it are really sparse. We just don't have very many open clusters with precise ages. So what we really need is ages for field stars. Like these stars, which I've shown many times in this talk already. These are rotation periods from Amy McQuillan's 2014 catalog. Something that I've been working on recently is using kinematics to get relative ages for field stars. And so let me just show you this plot. This is now these same field stars where I've gridded the stars up in log rotation period and temperature, and I've calculated the velocity dispersion of these groups of stars. And I've colored the stars by their velocity dispersions. Velocity dispersion is an age indicator. So you can think of color on this plot as being age. And this now reveals what's happening at old ages. So we can see that, let me break it down for you actually. Okay. In broad strokes, velocity dispersion increases with age. That's good. That means both kinematic ages and rotational ages are working as they should. This also reveals that the lower mass stars stay active longer. The lower mass stars are the dark purple ones here. They have large velocity dispersions. They're older. The reason I say they stay active longer is because even just being in this catalog of rotation periods, just being in that catalog means that you are at least a little bit active, as in you have dark spots on your surface and we can measure your rotation period. This is something we already knew. It's not new. We know that low mass stars stay active for longer. What is new is that these low mass stars seem to be spinning down more slowly than the higher mass stars. And that's a surprise, because lower mass stars have stronger magnetic fields. They have deeper convection zones, stronger magnetic fields, and they should lose angular momentum more quickly than their hotter counterparts. And that seems to be true for young ages, but for old ages, that's just not happening. So these are my models that I showed you earlier, and you can see that they cross colors, which means that they're not correct. They're not right. But let me just skip forward. These models from Spada and Lanzafame, in a sort of general sense, do actually capture what seems to be going on here. What they have in their models is they don't assume stars spin down as solid bodies. They say that the core is actually detached from the envelope. The envelope loses angular momentum, but the core continues spinning until a certain age, and then the angular momentum starts to resurface. And that's what causes the flattening off of their isochrones, and even causes this kind of dip feature, which is what we see in the kinematics. Okay. I think these models are kind of incredible because this is just based on clusters that are way down here, and then they're extrapolating upwards. And they seem, in pretty broad strokes, they seem to agree with what these observations now show. Okay, I'm out of time. I'm going to skip ahead. I wanted to say one more thing about Stardate, which is that it is a living publication. So it has an AJ paper and a Journal of Open Source Software paper. And that JOS paper is active and living. And that's one of the great advantages about publishing in JOS. The code can be updated. So we can take these models like the Spada and Lanzafame models and we can add them to Stardate. Okay, to summarize this section, rotational evolution is complicated, and core envelope coupling seems like it might be important, and we need to build that into our models. And then this final thing is that we can use kinematics to calibrate gyrochronology. This has never been done before. It seems like kinematics are a really useful tool for understanding rotational evolution.
What makes the delay in transferring angular momentum from the core to the surface? Because you said that after some age it actually
Yes.
occurs. So intuitively, what is behind that?
That's a really good question, and I think it's completely unknown. As far as I know, these are semi-empirical models. So what happens is they fit the models to certain data. These models were fit to young clusters. They seem to reproduce the observations. And so the assumption is that that is the physical process that's happening, but the interpretation of why that's happening is still currently unknown. Okay. Improving measurement precision. I'm not going to talk about it. I'm going to talk about it at ITC lunch because I'm out of time. Thank you very much.
Questions for Dr. Angus? In the back. Yeah.
Thank you for the talk. Really interesting. I had a question about, you mentioned the word pop stars a lot. I see a lot of your plots, they sort of don't go past like phase 1, 2 solar masses typically. So are these, do we see at least a similar trend in stars, say, up to say 2 solar masses in terms of like how well velocity squared can calibrate out gyrochronology and match with
Right, right. So gyrochronology is really applicable to stars with significant magnetic fields. So stars which have no convective envelope tend to have weaker magnetic fields. That's not true for all stars. So for example, blue stragglers, it might be possible to use gyrochronology to age date blue stragglers because some of them have magnetic fields. But to first order, most of those hot stars have weaker fields, and so they just don't spin down very much through magnetic braking. Yeah.
I want to make sure that I can see if there's people up here. No. Okay. Next question. Another one in the back.
I want to go back to something you mentioned when you were showing the multicolored plot of the Colloquium sample.
Mm-hmm.
Pointed out, you said something about the upper envelope being just a matter of activity bias, or bias in looking that we're seeing active stars. So my question is,
Oh, yeah.
Are you suggesting that that upper envelope is just due to you stop seeing the long periods anymore, or do you just stall it? Do you have an opinion there? So,
Yeah.
okay.
My opinion is that stars, there might be stars up here, and if they don't make it into the Macquillan catalogue, they are inactive. That is not necessarily true, because if they don't make it into the catalogue, they could have very non-coherent patterns in their light curve, so like very short spot lifetimes. But I'm assuming, and I have some basis for this, that if they don't make it in, they're just not active. And so I think, yeah, there's definitely something going on with this shape here. I think that is relevant. I think maybe this shape traces a Rossby number or something like that. That would be my prediction, especially because it's reflected in this shape.
Before I mentioned binaries as a possible irritant, but it seems that they might also add a kind of a separate way of doing some of these analyses. So for example, among eclipsing binaries, Max Moe and I found some really interesting ones where one star was evolved and the other was still, still sort of collapsing onto the main sequence. And so
Yeah.
the relative ages, one star serves as a guide to what's happening with the other. And with Gaia now available, to be able to help you find wide binaries, it seems as if, at least in some cases, the stars for which the methods do work may have exactly the types of companions for which you're still searching for answers.
Yeah.
So it seems to me that that might be a kind of an independent pathway where several elements of the fact that some of the more mysterious stars have companions can be used to shed light on their ages.
Yeah, absolutely. So I'm not sure that anyone's currently doing this with seismic stars as companions, but white dwarf binary systems are being used to calibrate gyrochronology. So there's a student working with me and BDNYC at the museum, and she's looking at white dwarf cooling ages. She's finding co-moving stars in Gaia. And also J.J. Hermes is working on this with Jen Van Saders. So that is, really one of the few ways that we can get precise ages for old stars is if they're co-moving with white dwarfs. So,
Well, maybe we can talk more about this next week.
okay, yeah, great.
Okay, I see 3 more hands. We have time for 3 more questions, so we'll go 1, 2, 3. Go ahead.
So it's
all of the relationships between age and period are empirical or semi-empirical. So my question is there any hope for building a physical model?
Yeah, so a lot of effort has been put towards building purely physical models, but they all end up having to be semi-empirical because there are just too many parameters that we just don't know. You could tune that. We just don't know what value they should take. So you have to fit them to the data. So like Steve Koala, Sean Matt, Mark Pinsino, Jen Pansadas, Subbu Mahanti, they're all developing these physical models that, you put in some sort of mass loss rate, some stellar wind pressure at the photosphere, you put in convection zone depth, but there are so many tuning parameters that it's very difficult to get a purely physical. Does that answer your question?
Yeah, I guess so. I guess I just want to maybe go a little bit further, like asking, like, is there like some data that would be helpful with doing that, like for astroseismically observed stars, like would you be able to, at least in one case, to do something more kind of?
Yeah. So with this astroseismic sample, make the picture more complicated again, and we have calibrated these relations to the astroseismic sample. The problem with astroseismology is that it's really incompatible with gyrochronology because you can get astroseismic ages for dwarfs if they're hot and if they don't have a strong rotation signal. And so the effort that's been done there's like 20 stars that you can use, and even those are questionable. The problem there is that if stars are old, I think this is really cool. If stars are old, I don't think they should appear in this catalog. So if stars are old, you should not be able to measure their rotation periods. If you find an old star and you can measure its rotation period, there's probably something strange going on. Like it has a binary companion, maybe it has a planet, a close-in massive planet. And so that's a problem with using astroseismology, although it has been done.
Aside from cases where you have a bunch of stars that are, for good reason to believe are coeval, and you can check the estimate you get for the ages of each against each other, do you have any, how independent can you get two methods on one star as a check on each other for the age?
That's also a good question. Typically, we haven't been that careful about this. So, for example, I used Persepi to calibrate my gyrochronology relation that's currently implemented in Stardate, but I used different stellar evolution models. So Persepi age, I don't know what stellar evolution models were used to calculate the age, but I'm using MIST models. And unless I use MIST models to go back and measure the age of Persepi, I'm not really comparing apples to apples. I think perhaps the details there aren't so important. There are other factors that increase the uncertainty more. But in general, there isn't very much care taken to use the same stellar evolution models to calibrate things. And it's hard to get around that model dependence. So I'm not really using models here. I'm comparing relative ages. I'm not using any model for the kinematic ages of stars, partly because I'm using VB and not VZ, which is a whole other thing. Yeah.
Hey, Ruth, you put a pin in my question.
Oh, yes.
I do really want to get your opinion about, you take Persepi and you extrapolate into one star of one age and one mass. You've now provided the tools to the community to get ages, so they're going to go and publish those ages. I really want your feeling, if we could just, if you don't mind putting up your plot and just tell me, what, if I go out and find a field star and it's an M0 and it's spinning at 80 days.
Yeah.
Do I really know the age to have a gig here?
It's a good question. I think this kind of summarizes the way I feel. The black lines are my models in stardates that are extrapolated from Persepi, and then the colors there show that, you know, these stars, these lines should curve down, right? They're not correct. This is a question of, are you going to get ages that are better than ages that you could get before, right? The models aren't perfect. They will not be perfect for a long time. Even the Spada and Lanza-Fahmy models are not perfect. It's very difficult to do this correctly. And it really depends on the science question that you're asking. These models will certainly rank stars by age correctly within a certain temperature bin. So I think there are caveats. I think as long as I make those caveats clear, if the community use the tool without paying attention to the caveats, then that's on them.
Does it work, like if I take the alpha Centauri system, I've got 3 stars, I know the rotation period for all 3. I don't know its age, I don't have like a mean, right? Radiometric dating, but is it relative, you know, do they all fall in one curve, for example?
I think so. I get confused between Alpha Cen and some other systems, but no, Alpha Cen's very cool, right? All of the stars are very cool.
Well, yeah, sorry, we don't have to do it here, but like Alpha Cen would be a G dwarf at 22 days, a K dwarf at like 33 days, and a mid-M at 83 days. So they all give you 5.28 years or whatever.
I don't know off the top of my head, but I expect the K and G would give you the same age. The M, the models aren't calibrated there. In mid-M, they're not really calibrated. So, I don't know. Yeah, I'm sorry, it's not perfect. It's not perfect.
No, it's not. I'm just saying that sometimes we have to conclude that a method which has a great promise simply isn't working out the way we hope. That's all. Rather than
Yeah. No, absolutely. I think this is a step along the path to stellar age perfection. And I think that we can get there, but it's going to take some work. But, you know, tools like this are still useful.
All right. Thank you very much. Let's thank our speakers. Mark specifically asked for a couple of postdocs to help us reassemble. If you don't mind moving.
Thank you.
You really have a nice effect when you're giving a talk
Oh,
like
good.
this. I can see that you're a good teacher.
Oh, thank you. Thank you.
So let's exchange email. We can figure out about getting
Okay,
together.
great.
I didn't realize that there was something like this where binaries could actually.
Yeah, oh yeah,
So I'd love to
definitely.
hear about what you're doing.
Okay, great,
And
yeah.
I'm not quite sure where I'm visiting though. So well, let's do the email and
Yeah,
see.
send me an
I
email.
want to talk to Jenna. I'm not sure what her plans are next week, but she's
Okay.
generally up in Columbia.
Right.
But I'd love to go to Flatiron. But if you're at the museum, I have an apartment not too far from the museum, so I can
right.
easily get there.
Okay.
So we'll
Okay,
discuss it.
sounds good.
Yeah, have a
I'm
great
so
day.
sorry. I'm going to need to whisk you away
Yeah.
in just a minute or two.
School good? I'm good. How are you? Good. Thank you.
What Dave asked, I guess if your uncertainties would reflect that, you know, is it perfect or not? Do these curves go, is the calibration for the gyrochronology the right one or not for different masses? Do you see that your uncertainties, the recorded uncertainties reflect these, that is worse here than no?
They could if I made them, but they
don't.
on their own they
So I'm
don't.
running on this issue. I'm doing a base. I told you in the
Yeah.
So I'm doing a Bayesian neural network to do not this, something similar, more for any age and mass and age, for any star, getting pretty much probably what isochrone pi does,
Yeah.
but maybe adding rotation. But the issue is that variationally, I'm using variational difference, and it gives you the uncertainties. And I get pretty good ones, or what I believe are good ones, but where you have no data is bad. But I was wondering, because here you're talking about regimes where you do have less data, or data that tells you, I don't know, like you're not doing great.
Yeah.
Doesn't that reflect, because I don't know the graphical model.
No, because it's a physical model that I'm extrapolating rather than something. It's not so data driven, right?
Okay.
So those machine learning methods are purely data driven. Where the data are not good, you don't predict the
Right.
ages.
Okay.
But for this,
You have
I
to-
calibrate something to data and I extrapolate.
Okay.
And so it
how
has.
do you get your uncertainties?
So the uncertainties come from the uncertainties on the observational parameters.
Oh, I see. So when you say Bayesian, it's Bayesian in that way, not in the way that it reflects the uncertainty of the model.
It doesn't reflect the uncertainty
I
of the
see.
model.
Okay.
It could.
Okay.
It could, but it currently does not.
Okay.
Yeah.
That's interesting. Okay.
Just doing, I'm so sorry.
Yeah, no problem.
I'll take your microphone off and you can leave it right here. Okay.
That's where I guys sit.
I don't actually. Just steal you. I just wanted to make sure you got a breather every time.
Oh, I am attached. Uh-oh.
What do you need? Are you tied up?
Yeah, I don't know how... Oh, there we go. I think I...
Turned it on here again.
Did I break this?